share the screen. All right, so we are here. I was going to do more problems from the word problems and maybe some 4.5. If there's time left over, I'll let you ask questions, but I'm not sure that's going to happen. Okay. Tomorrow, I was going to let you have the majority of the time to do a quiz, a curve sketch, the whole works, you know, domain, intercepts, symmetry, asymptotes, intervals of increase and decrease, maximum, minimum, you know, all that good stuff. Concavity, intervals of concavity, concave up, concave down, inflection points, and then sketch the graph. Okay, so that'll take a while. Okay, I might just introduce the last section, 4.8, but I still have next Monday and Tuesday to do 4.8. It hopefully shouldn't be that bad. Okay, I will give you a little bit of a heads up, okay, on the calculator. So 4.8 is very calculator dependent. Okay, you are at a considerable advantage if you have a button that says answer, ANS. So does your calculator have an answer button, ANS? If you do, it's going to be much easier to do the problems. Now you say, I don't have a calculator that has answer. You can still do it. You'll just be a little bit handicapped in that it'll take a little longer to do the problems. So, but I will, you know, conduct the class and let you get by with a calculator that doesn't have an answer button. So I'll be teaching you first section 8, assuming you don't have the answer button. So everybody will be doing the same thing. Okay. And then once I get going, those of you that have the answer button, you'll see how much faster it is to have a button like this. Okay, so does your calculator have an answer key like this? If you do, I'll show you. And if you don't, you can still do it. You'll still be able to do everything, but it's just going to be a little bit longer. Okay, so that's not until 4.8. All right, so I'm going to do some more of the word problems, which are applied maximum problems, and maybe some other curve sketches. Okay, so I've pre-planned. Okay, 4.737 is a nice problem. Okay, so let me show you what's happening with that one. 4.737. In case you're wondering, you know, you think about these problems, there's a lot more problems that we're not doing, as you can probably tell. Okay, so in the assignment, what? I am only, quote unquote, giving you these. Okay. But no question. I mean, look at all the ones that we're not doing, right? But if we did all of these, it'd take much, much longer, right? I mean, it's almost like you can spend the whole semester just doing problems like this. So that's why I'm intentionally picked only certain key ones. Okay, 37. A piece of wire 10 meters long is cut into 2 pieces. One piece is bent into a square, and the other is bent into an equilateral triangle. How should the wire be cut so that the total area is a maximum and a minimum? Okay, and for this, we're going to allow for the possibility that the whole thing is a square and the whole thing is a triangle. Okay, so this becomes maximizing and minimizing on a closed interval, way back in section 1, right? Where the wire is between 0 and 10, so the cut is between 0 and 10. And we're trying to maximize and minimize on a closed interval. Okay. So here we go. So the wire is 10 meters long. I think it was it meters? Or, yeah, meters. Okay, so I make a cut, which might mean no cut at all. Okay, so X is allowed to be anything between 0 and 10 inclusive. Okay, but in general, we'll cut here. So one piece is X, the other is 10 minus X, right? Okay, I'll take the 10 minus X, bend it into a square, which means each side is 10 minus X over 4. Okay. X, I bend it into an equilateral triangle, which means each side is X over 3. Is that all right? Okay, so one more time, pictures like this, I cut it somewhere, Could be here, could be here, could be wherever. Okay. How do I get the maximum area, the minimum area? So we're finding max and min on a closed interval between 0 and 10. Okay, so 10 minus x, bend it like this, so it's 10 minus x over 4. X, bend it like this, x over 3. So first I have to take a little time out, come up with a formula for the area of an equilateral triangle. This is area of an equilateral triangle. Okay, so this is a sidebar, so to speak. And everything from here to here. So let's have an equilateral triangle. Each side is S, S, S. Let me draw the perpendicular, which means this is half S. I'm trying to find H, so I can do 1/2 base times height. So H squared plus half S squared is equal to S squared. H squared plus 1/4 S squared is equal to S squared. Subtract 1/4 S squared. H squared is equal to 3/4 S squared. S squared minus 1/4 S squared is 3/4 S squared. Take the square root. Don't need a plus or minus. These are positive. So square root of 3/4 S squared. Square root of 3 is not nice. Square root of S squared, though, is S. Square root of 4 is 2. So the height is S radical 3 over 2. That's this height. And now I'm ready. Area is 1/2 base times height. So 1/2 the base is S. The height is S radical 2. S squared radical 3 over 4. So here's the formula for the area of an equilateral triangle. If you want it, you can put it on your cheat sheet, I suppose. It's not really that well known, I guess. All right, so I'm ready for the area function. Okay, so how do I find the area? So this is a square, so it's just a side squared. 10 minus x over 4 squared. And then for the triangle, it's s squared radical 3 over 4. S was x over 3. So x over 3 squared radical 3 over 4. Okay, so this is for the square. Maybe I would put a little square there and a little equilateral triangle there. Okay, so the total area is the area of the square plus the area of the triangle. Okay, a little bit of algebra. This is 1/16, 10 minus x squared plus x squared radical 3 over 36. 3 squared is 9, 9 times 4 is 36. And x is between 0 and 10. Okay, so I'm trying to maximize and minimize this quantity on a closed interval. This is a continuous function. So this is section 1, right? So that means I don't have to do the second derivative. First derivative is good enough. Okay, I do have to plug in the endpoints, 0 and 10. Okay, so if I plug in 0, that's gone, right? That's gone. Put a 0 here. I have 10 squared over 16. 100 over 16, 25 over 4, that's 6.25. That's if the whole thing is a square. Okay, the other extreme, a of 10, if I put 10 here, that's gone. That means the whole thing's a triangle. So put 10 here, it's 100 over 36 radical 3, 10 squared radical 3 over 36, 25 radical 3 over 9, punch in my calculator, 4.81 roughly. Okay, so if I bend it so the whole thing is a square, 6.25. The whole thing's a triangle, 4.81. Okay. Now I look for critical values. Okay, so I need to take the derivative of this guy. So the derivative is 2 times 1/16, 1/8, 10 minus x times -1, the derivative of the inside by the chain rule. So 1/8, 10 minus x times -1. The derivative of this, 2 comes down, 2 over 36 is 1 over 18. So x radical 3 over 18, set it equal to 0. Okay, so clean this up. -1 times that, just turn it around, x minus 10, right? So x minus 10 over 8 plus x radical 3 over 18 equals 0. Don't like the fraction, so I multiply both sides by 72, common denominator. 0 times 72 is 0. So 9 times x minus 10 plus 72 divided by 18 is 4. 4x radical 3 equals 0. Distribute 9x minus 90 plus 4x radical 3 equals 0. throw the 90 on the other side, add 90. And then these two both have an x, factor out the x parentheses 9 plus 4 radical 3. Divide both sides by this weird thing. So x is 90 over 9 plus 4 radical 3. Punch it in your calculator, about 5.65. Okay, take that weird thing, plug it into the function over here. Okay, and I got 2.72. And I notice 2.72 is smaller than 4.81, also smaller than 6.25. Okay, so the absolute maximum is at x equals 0, which means the area is 6.25. That means the whole thing is a square. And this should be meters squared, of course. The minimum is when I make the cut at x equals 5.65 meters, the area would be 2.72 square meters. Okay, so that was problem 37. Okay. All right, then problem 25, and that was the last one I was going to show you for now, unless I have a lot of time later. Find the dimensions of the rectangle of largest area that can be inscribed in a circle of radius r. Okay, so what do they mean by that? Okay, circle of radius r, I set it up at the origin. X squared plus y squared equals r squared. That's a circle of radius r. Okay, a little bit of algebra. Y is equal to radical r squared minus x squared. Okay, so they're talking about draw a rectangle like this. How can I make the biggest rectangle? Okay, that fits like this. So obviously you want to expand it as much as you can. You know, touch the four corners will touch the sides. Okay, you can see I can make a very small area if I kind of go like this, right? I make it like that, or if I make it very tall but not very wide, right? I don't get very much. Okay, so this is x comma y, which means this whole thing is 2x. This whole thing is 2y. So I'm trying to maximize the area, which is 4xy. All right, so how do I maximize the area? So I have 4xy, but y is equal to radical r squared minus x squared. So here we are. A of x is 4x radical r squared minus x squared. X is between 0 and r. Okay, incidentally, you can tell what happens when you plug in 0, 0, no area. What happens when you plug in r? R right here, that's 0, no area. So those are two extremes. If you have it all horizontal or all vertical, so to speak, well, you're going to have 0 area. Okay, so I have to differentiate this mess, which is not very nice. So A prime, okay, pretend this is r squared minus x squared to the 1/2 power. By the way, r is considered a constant, some constant. So first, 4x times the derivative of the second. Derivative of the second is 1/2 r squared minus x squared to the negative half times the derivative of the inside, which is negative 2x. Okay, that 2 is going to cancel that 2 later. Plus second function, radical r squared minus x squared, times the derivative of the first. Derivative of 4x is 4. And I'm trying to set that equal to 0. Okay, a little bit of cleanup here. X times that x is x squared. I have a negative and a 4. And this thing to the negative 1/2 means square root on the bottom. Plus that. Okay, set it equal to. All right, that looks like a lot of work. Move that over. 4 radical r squared minus x squared equals 4x squared. I can cancel the 4's. Right, divide by 4. And then multiply both sides by radical r squared minus x squared. These cancel out. What's radical r squared minus x squared times another radical r squared minus x squared? r squared minus x squared. Very nice. Equals x squared. Okay, remember r is a constant. I'm solving for x. So add x squared, r squared equals 2x squared. Solve for x, not for r. R is a constant. Divide by 2. Okay, so coming over here, x squared equals r squared over 2. Take the square root of both sides. X is r over radical 2. Okay, I plug back in for y. Y is r squared minus x squared. So r squared minus x squared. If I square this, I have r squared over 2. R squared minus r squared over 2 is another r squared over 2, which is r over radical 2. Okay. And I know I'm going to get a positive area. Okay. So I actually don't have to do a sign chart. I sort of already did a sign chart. Because you know how you would normally pick something on both sides? Okay. Well, I already know when I plug in 0, I get 0. Plug in 0, you get 0. Plug in r, you get 0. This will not be 0, it's positive. Therefore, it's a maximum. Okay, so I have what I want. Now, r over radical 2, that's the same as radical 2 over 2. Okay. So as you might guess, that's a square. So x and y are both radical 2 over 2. But the problem asks for the dimensions. The dimensions are double the x and double the y, which means they're both radical 2 over 2. I should forgot to put the r there. Okay. So radical 2r by radical 2r is the final answer. Okay, so x is r over radical 2. That's the same as radical 2 over 2. Same with y. But the question was, what are the dimensions of the circle, of the rectangle? So this is radical 2 over 2r. This is another radical 2 over 2r. So you have 2 of them. So the best final answer is radical 2r by radical 2r. In other words, it's a square. Okay. All right, so that was 25. Okay, let me go back and do a curve sketching one. I was going to show you problem 45. 5. Let's see, page 322. Y equals 1 over x plus natural log of x. Okay, section 4.5. Section 4.5. Okay, for differentiation, I treat that as x to the negative 1 plus ln x. Okay, domain, you can't have 0. Well, natural log, you have to have a positive quantity to plug in, so the domain is from 0 to infinity. So whatever the graph looks like, it can only be in quadrants 1 and 4. Okay, I'll just show you quickly the final result, but nothing in quadrant 2, nothing in quadrant 3. Turns out not to have anything in quadrant 4 either, but we don't know that ahead of time. But all the graph is from 0 to infinity. Intercepts, x equals 0, not allowed. Y equals 0. 1 over x plus ln x. We can't solve that by traditional means. Okay, there's no way to do that. Okay, so don't worry about it. Okay, then, actually I made a mistake here. Okay, symmetry. You can't have any symmetry because you can't have any reflection. There's no graph in the other quadrants, right? So we already know that's impossible, so forget about it. Okay, symmetry, none. Asymptotes. Okay, when x goes to infinity, this gets big, this approaches 0. 0 plus big is big. Okay, so when x approaches infinity, y approaches infinity. Okay. We do have to consider what happens when x approaches 0 from the right, though. So we need to consider this. Limit as x approaches 0 from the right of 1 over x plus ln x. Okay. In order to do that, I got a common denominator. So made this x over x. So multiply this by x over x. 1 plus x ln x over x. Okay, so what happens when x approaches 0 from the right? So I have to take a little time out and work only on this. So what's the limit as x approaches 0 from the right of x ln x? I want to use L'Hopital's rule, so I force it. So multiplying by x is dividing by 1 over x. And now this is infinity over infinity. When x approaches 0 from the right, ln x approaches negative infinity. If you plug in 0.0001 here, that approaches positive infinity. So it is infinity over infinity. So I can do L'Hopital's rule. The derivative of the top is 1 over x. Derivative of the bottom, treated as x to the negative 1, is negative x to the negative 2. Okay, x and negative 2 can go upstairs. X comes down, minus. So negative x squared over x. That's the same as negative x. So when x approaches 0 from the right, negative x approaches 0. Okay, so this whole thing is 0. This limit is 0. Okay, so now getting back to this expression. So when x approaches 0 from the right, this thing approaches 0. That's what I need to take a time out for. Okay. So if this approaches 0, I have 1 plus 0 divided by 0.000001. So that approaches infinity. So that means graph approaches infinity on this side and also this side. Okay. And now we're ready for our calculus. So take the first derivative. The derivative of this is negative x to the negative 2 plus 1 over x. I'm going to write this as x to the negative 1. This is better for calculus. This is better for algebra. Negative 1 over x squared plus 1 over x. Double prime. Derivative of this is 2x to the negative 3rd minus x to the negative 2, which for algebra should be written as 2 over x cubed minus 1 over x squared. Okay, set y prime equal to 0. Y prime was that. Negative 1 over x squared plus 1 over x equals 0. Set that equal to 0. I don't like the fraction, so multiply both sides by x squared. X squared times negative 1 over x squared is negative 1. X squared times 1 over x is x. 0 times anything is 0. So that looks like x equals 1. And it should be 1 comma 1. Made a mistake there. You plug in 1. 1 over 1 is 1. ln 1 is 0. So 1 comma 1. Do my sign chart. Y prime is negative 1 over x squared plus 1 over x. Okay, there's not any really nice numbers here, but you can plug in a half. If we plug in a half, it's negative 4 plus 2, which is a negative quantity. If I plug in 2, I have negative a quarter plus a half. That's actually positive. Okay, so positive. So this one, there's no real nice way to do it except just multiply it out. Okay, so decreasing, increasing. So f is decreasing between 0 and 1. I can't say negative infinity. That's not in my domain. Domain's only from 0 to infinity. And then increasing from 1 to infinity. So 1, 1 is a minimum. In fact, it's an absolute minimum. I made a mistake here. I had it come down to touch the x-axis. It doesn't. It should be more like this. So that clinches that there's no intercept either. This should be 1, 1. Sorry. All right, so 1, 1's a minimum. Okay, second derivative analysis. Set y double prime equal to 0. So my double prime was this guy. So set that equal to 0. And once again, get rid of the fractions. Multiply both sides by x cubed. X cubed times that is 2. X cubed times that is minus x. 0 times anything is 0. That gives me x is equal to 2. Plug in 2. 2 comma 1/2 plus ln2. Not very comfortable. Okay. See, this is about 0.6, 0.5, so it's about 1.1 roughly. 1.193, I think. All right, sine chart. Lay down the 2. Plug in 1. 2 minus 1, positive. Plug in 3. Okay, I have 2 over 27 minus 1/9. That's a negative quantity. Okay, this is like 3 over 27, right? So 2 over 27 minus 3 over 27 is negative. Okay, concave up, concave down, inflection point. All right, so we got it. Function is concave up between 0 and 2, concave down from 2 to infinity, and 2 comma 1/2 plus ln2 is an inflection point. So here we go. It goes to infinity there, goes to infinity there, minimum at 1, 1, inflection point, decreases, increases, decreases between 0 and 1, increases from 1 to infinity, concave up, U-shape from 0 to 2, the rest of the time concave down, but still going to infinity. So there we go. Okay, so that's problem 45. Okay, and I'll go ahead and do a couple others that I had already done due to office hours. 4.525. Y equals x over radical x squared plus 1. Okay, so let me show you that one. See, what time is it? I'm not sure I'll have time to let you ask questions, but we still got next week. Okay, y equals x over radical x squared plus 1. Domain. Okay, it is a fraction, so I have to be careful that I'm not taking the square root of 0 or of a negative, but that's not possible. Look at x squared plus 1. X squared plus 1 is always positive. It can never be 0. I can take its square root. So the domain is all real numbers. Intercepts, plug in 0, you get 0. 0, 0. Symmetry. Replace f of x with f of negative x. Put a negative x there, a negative x there. Negative x over square root of negative x squared plus 1. But negative x squared is the same as x squared. Okay. And now, how does this compare with the original? It's the opposite. Negative f of x, okay, which means I have an odd function. I have symmetry with respect to the origin. Okay, asymptotes. There are no vertical asymptotes. In order to have a vertical asymptote, you'd have to have undefined values, but there aren't any. Okay. Horizontal asymptote. What happens when x approaches infinity? Okay. By the way, this is infinity over infinity, but L'Hopital's rule wouldn't really help because taking the derivative of the bottom, you end up with something just as bad as the original. But we did play this trick before. Okay. So ignore the red temporarily. X approaches infinity. X over radical x squared plus 1. Divide top and bottom by x. So in red, I divided by x. I divided by x in the form of x squared underneath the radical, right? X squared underneath means same as divided by x outside. So this becomes 1. 1 plus 1 over x squared. Okay. Now when x gets super big, this approaches 0. So you have 1 over radical 1 or 1. So y equals 1 is a horizontal asymptote. So y equals 1 is a horizontal asymptote. And because I already know I have symmetry, so by symmetry, y equals negative 1 is also a horizontal asymptote, since I already know that I have symmetry with respect to the origin, right? Okay. So whatever happens over here, I got to have something equivalently happening over here. So y equals negative 1 is also a horizontal asymptote. Okay. Or we can take the limit as x approaches negative infinity, but we don't have to. We can just argue by symmetry. All right, now the first derivative, you can tell it's not going to be very nice offhand, but strangely enough, it actually comes out to be pretty good. Okay, so x over radical x squared plus 1. So quotient rule. Bottom times derivative of the top. Bottom times derivative of the top. Derivative of the top is just 1, so I don't have to do anything. Minus the top, x, times the derivative of the bottom. The bottom is x squared plus 1 to the half. So x times 1/2, x squared plus 1 to the negative half, by the chain root times the derivative of the inside, which is 2x. And then, all over the square of the denominator, well, what happens when you square a square root? You just have x squared plus 1. Believe it or not, this whole thing comes out nice. Okay, let me see if I can show that to you. Cancel the 2's. So I have radical x squared plus 1 minus, let's see, x times x is x squared on top. The 2's are gone. This means square root on the bottom, square root of x squared plus 1, all over x squared plus 1. Okay, so right now I have this. Okay. Believe it or not, if I multiply by radical x squared plus 1 over radical x squared plus 1, it comes out really, really nice. Because what's that times that? X squared plus 1 minus that times that. Well, that cancels out. You just have x squared. X squared plus 1 to the first power. X squared plus 1 to the 1/2. Grand total of 3/2. 1 plus a half. The exponent is 1. That exponent is a half. You have the same base. So x squared plus 1 to 3/2. Notice x squared cancels out. So I simply have 1 over x squared plus 1 to the 3/2 power. Very nice. And I notice this expression is greater than 0 for all x. Right? What do I know about x squared plus 1? Positive. Positive raised to the 3/2, positive. 1 divided by positive, positive. Always greater than 0. F is increasing for all real numbers, from negative infinity to infinity. I don't need a sign chart. F is decreasing nowhere, so there's no max or min. That's nice. I don't have to worry about that. Okay, so I do the second derivative analysis now, but at least taking the derivative of this is not so bad. So the derivative of this is negative 3/2, x squared plus 1 to the negative 5/2, and then times the 2x. So here we go. Negative 3/2, x squared plus 1 to the negative 5/2 times 2x. 2's cancel out. Negative 3x over x squared plus 1 to the 5/2. Set it equal to 0. Okay, when is a fraction equal to 0? Top is 0. So x equals 0. 0, 0. Okay, now I do have to have a sign chart, but this sign chart is very easy. Okay, I didn't even bother putting down any numbers because it should be quote unquote obvious. Okay, so I put down 0. Look at the denominator. The denominator is always what sign? Positive. So the sign is completely determined by the numerator. So plug in negative 1. Negative 3 times negative 1, positive. Positive 1. Negative 3 times positive 1, negative. Second derivative positive, concave up. Second derivative negative, concave down. So f is concave up from negative infinity to 0. F is concave down from 0 to infinity. So I have an inflection point at the origin. And here comes the whole graph. Okay. Always increasing. Asymptote, asymptote. Increasing concave up, increasing concave down. So there we go. All right, so that's that. And let's see, another one that I already did, somebody during office hours, was in 4.7, so I'll knock that out of the way. 4.711. So let me show you that. Consider the following problem. A farmer with 750 feet of fencing wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle. What is the largest possible total area of the rectangle? Okay, so the picture is like this. I don't have enough hands to get it all. Okay, so you have 750 feet. There are 4 pens, 1, 2, 3, 4, and it looks like this. Okay. I'm not going to worry about A, B, C, D, E, F. As far as I'm concerned, the problem stops right here. What is the largest possible total area of the 4 pens? Okay. If I do the problem, I'm actually answering A, B, C, D, E, F. So we're just going to go with this. Okay. So here's my picture. So what's the largest possible area? Don't worry about A, B, C, D, E, F. We're going to do the problem. In the process of doing it, we're answering the question. Okay, so I'm going to call that X and call that Y. There are 1, 2, 3, 4, 5 X's, and there are 2 Y's. Okay, the grand total of fencing is 750. Okay. All right, so area is X times Y. I'm trying to maximize the area. So we're going to have 1, 2, 3, 4, 5 X's plus 2Y equals 750. Remember, solve for Y. So Y is 750 minus 5X, right? Subtract that and divide by 2. So Y is 750 minus 5X over 2, or 375 minus 5 halves X. 750 divided by 2 is that, minus 5 halves X. Okay, plug that back into here, so you have a function that only involves X. So A of X now is X times Y, but here's my Y, right? 375 minus 5 halves X. Multiply it out, 375X minus 5 halves X squared. Okay, and that's what I want to maximize. With the constraint that X and Y are positive, right? I don't want 0, I don't want any negatives. So if I have 0 or negative, throw it out. Okay, so do my derivative stuff. A prime, 375 minus 5X. 2 comes down, hits the 5 over 2, 5X. Second derivative is negative 5. That's less than 0. Less than 0 means concave down. So when I have a horizontal tangent, slope of 0, I will have a maximum. Am I looking for a maximum? Yes. Okay. And again, it always works out the way you want it. If you're looking for a maximum, it'll be a maximum. If you're looking for a minimum, it should be a minimum. But you want to prove it. You can prove it often with the second derivative. Okay, set A prime equal to 0, which means horizontal tangent on the graph. So 375 minus 5X equals 0. A little bit of algebra. X is 75. Okay, then plug back in to find Y. Y was that, right? So Y is 375 minus 5 times 75 all over 2. It comes out to be 187.5. Okay, so the dimensions that maximize the area, this time it's not a square. Quite often say, okay, it's got to be a square. Not this time. To maximize the area, you don't make it into a square. You make it like this, 75 feet by 187.5 feet. Okay. That's not the answer, though. The answer was, what is the maximum possible area? So I just multiply these two together for the maximum area, 14,062.5 square feet. And that's my answer. Okay, we're done with this problem. I'll dig just a little bit deeper about the square thing. Okay, so to maximize it, if the picture is going to look like this, right? You don't maximize the area by making it a square. And that kind of makes sense because you have to draw more lines this way, so you run out of material faster. Okay, but I will say this, kind of curious, 75 feet for X, right? So how many X's are there? There's 1, 2, 3, 4, 5. Okay, so 75 times 5 is 375. Okay, you don't have to write this down. I have 2 Y's, 2 187.5s. If you do 187.5 times 2, it's 375. Okay, so in other words, you don't make it into a square, but you have as much material horizontally as vertically. Okay, so another way of thinking of it is, okay, you got 750 feet, right? Divided by 2, 375. So the idea is you make 375 this way, And you also make 375 this way, okay, which is 375 divided by 5 is 75. Where'd it go? Right. And then 375 vertically, 375 divided by 2 is 187.5. So it's not a square per se, but you dedicate just as much material horizontally as you do vertically. Okay, so that's just a side note. That has nothing to do with the problem, but it's just a curiosity, I guess. Okay, and that was all I was going to demonstrate today. We only have a few minutes left. Let me stop the share and see if we have anything in the chat. Okay, so I don't see anything there. Okay, 8 minutes left. You want to ask a question, but I can only answer it within 8 minutes or so. Otherwise, we can just stop. Okay, and I'll blab a little longer. So tomorrow, I was going to introduce the last section, 4.8. Okay, and again, if your calculator has the answer button, A and S, you're better off than if you don't have it. So yeah, so I'll introduce that, but then most of the rest of the class tomorrow, I'll let you work on just one curve sketch, just the one, but as you know, sometimes just doing the one takes a long time. Okay, so anybody want to ask anything? Otherwise, we're done for the day. Okay, so that'll be it, folks. So have a good day. So tomorrow I'll introduce the next section, and then you'll have the rest of the time for the quiz. All right, have a good day, everyone. See you later. Bye.